Okay, so now we'll actually compute the Gaussian width of this set of very concentrated vectors, right? What we saw before is basically if M is a lot bigger than the square, right, up to constants of this, then A with Gaussian entries are M times N with say Gaussian entries. I mean, the scale doesn't matter. IID entries will, with high probability, satisfies their IP, satisfies S null space property, right? And in particular, then this implies that if it satisfies the null space property, then we know that we can do exact recovery, right? So all we have to do is to compute the Gaussian width of this, right? Of course, we already know, I mean, it's worth pointing out that, right, the Gaussian width of this will for sure be bigger, right? The Gaussian width of this will be bigger than the Gaussian width of sparse vectors, right? Because the set is contained in the set of sparse vectors is contained here, right? If a vector is as sparse, then in particular, right, if we just pick that to be its support, this is bigger than 0 and this is 0, right? So for sure, that's at least we know. Okay, but so let's compute this. Right, so this expected value of the max over V in the set of G transpose V. Okay, so now, of course, we can, without loss of generality, okay, maybe I should say, the largest, the optimizer for V will for sure, put the terms with the highest absolute value together with the terms with highest absolute value in G. Right, so we can take S, we can take, say, without loss of generality to make things simpler. Without loss of generality, let's say we take G to be ordered, right? Just so that I know what is the vector, the subset S that I'm going to need, right? Let's say I'm going to do this, right? The definition of this is coordinate independent, right? In the sense that if I permute the coordinates, nothing changes. So I can do this, right? So I draw G and then I just reorder it to have it like this. Then, right, what is this? Then this is expected value, right? The max, right, of V still in a set. And now I know what is the set, right? Because the set S will just be the first coordinates, right? I can set, I can set V, the set S is simply going to be the versed S coordinates, right? Because those are the largest entries of G. And now, of course, V is going to be in the sphere, and V of S, L1 norm, is going to be bigger or equal than V outside of S, L1 norm. Right, and now what we have, well, we can write it like this, GS VS plus GS complement transpose VS complement. Right, where S, I mean, here I ordered it just to make, just to make things simpler, but you could also just say that the set S is the set where the largest, V is the largest in absolute value, right? This will be all the same. Right, so now let's try, how can we make sure this is small? So what's going on, right? What's going on is the L1 norm of this is very, very small, right? That's the thing that we do know, right? Is that the L1 norm of this is very small. Okay. How is it, so if we control, right? If we control the L1 norm of this, right? So let's think about this, about how we're gonna bound this, right? So if here, right? V is norm 1, so this is at most norm 1 in L2 norm. All right, so now the norm of the largest, so this will be smaller or equal for sure than just the norm of GS, the 2 norm. Right, and we've seen when we did the calculation for sparse vectors that this is around square root S, square root log n over S. Right, and so like that's already around the right term. But here, if we do that, the L2 norm of this can potentially be too big. But what we know is that the L1 norm of this is very small. Right, and so in particular, if I have an inner product like this, then this needs to be smaller or equal, right? Okay, so maybe because this, the L2 norm of this is smaller than 1, this term will be smaller than this. Now, what I have control of is the L1 norm of this, but an inner product is smaller or equal than the infinity norm of this times the L1 norm of this, right? Just think of the products, right? We get the sum of the absolute values here. The largest thing is the L1 norm. The largest thing we could get is if this was always the biggest and its sign always matched the sign of this. And so we would get exactly as complement infinity times the L1 norm of C. Okay, so let me go over here to write this again. Okay, so let's see. So we have GS transpose VS plus GS complement transpose VS complement. Okay, this is smaller or equal than, right? So what we have a control here is of the L2 norm, right? We don't really have a good control of the L1 norm because all we know is smaller. So then we can just do this, right? Times, say, the L2 norm of S plus the L infinity norm times L1 norm. Okay, so far so good. Now, of course, this is smaller or equal than 1, right? But now the question is, how do we control this, right? How do we control this norm? All we know is that this norm is smaller or equal than the norm, right? By the property. But now, you know, L1 norm can sometimes be much bigger than the L2 norm, but only if the vector is very large. If we're only talking about as components, then Cauchy-Schwarz, right, gives us that this is smaller or equal than the size of S, which is square root of little s, times the L2 norm of this, right? The L2 norm of this we know is smaller or equal than 1, so this is smaller or equal than square root s. So we get a bound for this of square root s, and this is the this is the bound where we're really using the property, right? Because the L1 norm of something that has around n coordinates could potentially be square root n, not just square root s. So we get immediately that this quantity, right? So the Gaussian width of CS is smaller or equal than this expectation, right? This max over S. And now we get, but we'll just pick the largest entry of G, we get the 2 norm of the biggest S entries plus plus square root S times the largest entry, right? Times the largest entry outside. Maybe let me take this off and not be on top of each other. Right, and so now this is easy to control. Right, now it's just about properties of Gaussian vectors. Right, we've seen already that, you know, the expected value. So it's clear what the maximum is going to be, right? You're just going to pick the largest entries of G, the largest entries in absolute value, right? Or in particular, you know, if I order the vector, I'm just going to pick the first ones. So I know that GS2, this we saw when we looked at the Gaussian width of sparse vectors, this will be something like square root S, square root log n over S. And now I have to ask myself, what is the typical value of this, right? When I take the largest entry of all the rest of the vectors, right? Basically I'm taking the S plus 1 largest entry, right? And it's not hard to see that also the value of this will be like square root log. You can either do the union bound, or you can notice that, right? You can just notice that this would be, you know, like this is basically the mean value for the entries, the first S entries, right? So the S plus 1 cannot be bigger than this, right? This is when I take the S plus 1 largest Gaussian entry, this is its value, right? 2 ways of proving it. You can think of here, right? If all the S entries were much bigger than this, then it couldn't have been that L2 norm was this. That's one way. Another way is just to use the union bound. But right, because what you need to have is S entries bigger than that, and if you look at all possibilities of N entries, you get this N choose S, and you pick up this log. So this means in particular that the Gaussian width of these concentrated sets is smaller or equal up to constants of square root s, square root of log n choose s. Right? So we get exactly the same behavior as the Gaussian width for sparse vectors. And immediately we get this amazing theorem, right? We've already got an amazing theorem that says, right, if m is much bigger than the square of that, so if m, or I should say, there exists a positive constant. Let me do this a bit more carefully. There exists some constant, some universal constant, right? I mean, we can compute this, but I'm not going to worry with it for now, such that if m is bigger or equal than c times s, right? We need to take the square of that. So times s log n over s, then a with IID, say N01 entries, satisfies the S null space property. And in particular, it means that it's a good matrix for compressed sensing, right? Then we get immediately that if we do L1 optimization, we actually recover the sparse vector, right? And so with this, I hope that I was able to convey that, you know, Gordon's theorem is extremely useful. You can use it in many, many different settings, right? And by taking the Gaussian width, not quite of the sets that you're measuring, but something a bit bigger, right? This set of concentrated vectors, we're able to prove not only that our matrix separates the vectors we want to see, but actually that an algorithm will find the vector just from the measurements. Right, and so this is one of the main results in compressed sensing. This is not usually the way that it's presented. Right? It's not usually the proof because one doesn't. Right, we did Gordon's theorem before, so we have this big tool that we can use. But with this, we get immediately a theorem saying that you know, that compressed sensing will if a random matrix will work for compressed sensing, and we know it satisfies our IP, the null space property, and so on. Okay, thank you.